3 is entitled Stoichiometry. If I had my way, I would author this unit to be formula analysis and spectroscopy. If you recall, in honors chemistry, we didn't study stoichiometry until after Christmas. But in AP, we dig right in because we are going to be applying the concepts that you're reminded of and the problem solving throughout this entire course. This video will refresh you on some foundational terms, introduce mass spectroscopy, review how to calculate average atomic mass, and remind us of this central concept in chemistry, and that is the mole. So, to dig in, foundational terms. We often interchange these terms, but they are different. Now, atomic mass is kind of a cop-out. Whenever we, as AP students, use this term, we need to attach the adjective of average. Because really, if we just say atomic mass, it's kind of mass number. Mass number is the result of the count of protons and neutrons. So we know that the protons and the neutrons deliver the mass for the atom, and a proton is assigned 1, a neutron is assigned 1. You already reviewed how you determine, given mass number and atomic number, the number of subatomic particles. Average atomic mass, that is the weighted average of the isotopes taking into consideration their percent abundance. We're going to learn how to calculate that in a moment. So the values on the periodic table that are reported past the decimal place, those are average atomic masses. And we are going to report these to the 100th place, rounded to the 100th place. If we do that, we are utilizing these average atomic masses. So for example, for oxygen, if we report 16.00, that's the average atomic mass. Where if we round to a whole number, that's the mass number. If we would do, let's say for phosphorus, if we would round it to 31, that's the mass number. But 30.97, that is the average atomic mass. Now what about unit? Now we know for most of our practices that we assign a G for gram. This is the mass, but as we're going to remind you in a moment, this would be the mass of oxygen atoms that would be in 1 mole. Remember, a gram feels like a paperclip in your hand, so 16 paperclips, 16 grams, would definitely not be 1 atom. That would be a mole of atoms. However, there's an atomic mass unit, an AMU. And that is then the mass assignment for the average oxygen atom. So AMUs are used to reference individual atoms, but grams would be a mole of atoms of that element. So only really in this chapter will we see AMUs, because when do we ever practically deal with individual atoms? We will attach grams. The basis of all the values on the periodic table, the carbon-12 isotope was assigned to be 12 AMUs. And all the other values are assigned based upon that reference. So that is our reference point for masses. That's just good to make note of. All right, how do we even know that there's isotopes, that there's different versions of every element? Well, that's what mass spectroscopy does for us. A mass spectrophotometer, I really like this image. Let me get a little bit more in focus. So, what you would do if you're analyzing samples of an element is you would inject your sample of copper or sample of helium. Usually it's vaporized, and then, or it would be vaporized, and then the element sample is ionized. So they send electrons through it to create ions to actually knock electrons off, and so we have positively charged ions. And ions things that are charged respond to a magnetic field. And so they place them between two very strong magnets, and based upon the different masses, those isotopes get separated. And the result is usually portrayed in a graph. For example, if silver was analyzed, there are two most common isotopes, and we're going to get two peaks for the different masses, but we also know that every isotope is not found in equal abundance. We're usually going to find one of the isotopes more commonly, so it's going to have a greater intensity when it hits the detector, which can be translated into a percent intensity or a percent abundance, or even a ratio of the number of atoms of that version. So we can see that we have two isotopes of silver, and this 107 isotope is found less than the 109. Here, chlorine, 35, definitely found more than the 37. So here are just on your student packet the analyses of neon. Now we can see there is 1, 2, 3 peaks. So that means 3 isotopes for neon. But the version that has this mass is much more abundant. It hits the detector with a much stronger beam, so that is translated into a percent intensity or a relative number of atoms. And so this is taken out of 100. So it's just a different interpretation of the same data. So we can see out of about 100 atoms, 91 would be neon 20, then 9 would be neon 22, and then less than 0.5%, or is that 3? I think it's 3%. Would be neon 21. Okay, so these are taken into account. This is how we get the data that we eventually use to be able to calculate average atomic mass. It is a weighted average, taking into account the percent abundance of each of our elements. So what we're looking at here is a question where we're given mass spec data. So we need to be able to pull data from mass spec results, but also answer questions like these if given a mass spectra. All right, how do we know if it's mass spectra? Well, for us in AP Chemistry, it only will be an analysis of a sample of element. We won't be dealing with compounds. That's for later chemistry. And it's going to be a graph of number of atoms or percent intensity or percent abundance versus mass. That's how we know it's a mass spec. Okay, so what we're being asked to do here is to calculate the average mass, which we know this would be average atomic mass of copper. So we have two versions, copper 63, copper 65. So we know we can write our isotope like that. We could also do a nuclide symbol. So we know our mass is to the upper left, and then the atomic number would be to the bottom left, which was 29 for copper. Okay, so we could do it that way or this way. I like to then place the percent abundance next, which it's a relative number of atoms. So I could say, since it's out of 100, it's 69.09%, or I could say 69.09 atoms out of 100 atoms. And then my individual mass for this isotope, and the copper 63 is 62.93 AMUs. See, again, we're talking about the mass assignment for a single atom. And then this I'm getting is 30.91 atoms per 100. And this is 64.93. Okay, so a weighted average. We are going to multiply the individual mass assignments by their percent abundance, or ratio out of 100 in this case. So I'm going to base sig figs, and I'll just put my answers over here. Let me just get that. Yeah, you can see it a little bit better. And I would get 43.48, and I'm still carrying my unit of AMU. I would get 20.07, still carrying the unit of AMU. And I add these, 63.55. So this is the weighted average. This represents the mass of the average copper atom. Now notice, not one copper atom actually has that mass. It is a weighted average taking into account the percent abundance. So let's see, I have a 63 version and a 65 version. So can we see that the average is closer to 63 because we are going to encounter that version more often. All right, so reading through these, if you want to pause, we'll talk about these more together. So we wanted to get the method of calculating first. All right, so moving onward, the star, the mole. We know in chemistry the mole is our counting unit. So just like a dozen, where a dozen means 12, and you can have a dozen of anything. Well, a mole means Avogadro's number. And you can have a mole of anything, just like you can have a dozen of anything. 1 mole is equivalent to 6.022 times 10 to the 23rd of that thing. So if you have a mole of pencils, you would have Avogadro's number of pencils. If you had a mole of marshmallows, it would be Avogadro's number of marshmallows. But this is a crazy big number. So remember in honors chem, we would do thought experiments, like a mole of marshmallows would cover the surface of the earth to a depth of, I'm not sure what it is, a mile or something like that, or 1.5 kilometers. But we need a crazy number of them to be able to work practically in laboratory situations because, of course, of the size of the atom. If we have 1 mole of element, for example, helium, well then we have Avogadro's number of those atoms. So 1 mole of element, it would be Avogadro's number of atoms of that. And that, of course, is equivalent to the average atomic mass. And because I'm talking about moles, then I would put a gram on that. All right. But we can have a mole of other things in chemistry. For example, what if I have 1 mole of water? Well, a mole means Avogadro's number. But this is a compound that is made of hydrogen and oxygen elements, atoms of those elements. If I have a mole of the compound, it's Avogadro's number of the smallest piece of the compound. Water is covalent, made of just nonmetals. The smallest piece of a covalent compound is a molecule. So I would have Avogadro's number of molecules of water. What would the mass of that? Well, that's where formula mass or molar mass. Now, of course, we could use molar mass to be talking about average atomic mass, because this would be the mass of 1 mole, in this case of the element. But usually, in chemistry, we use molar mass to denote the mass of 1 mole of a compound. So we usually use these terms interchangeably. So what we would do in water, we have hydrogen and oxygen, and we have 2 hydrogens, 1 oxygen. The average atomic mass of hydrogen, we're okay most times to go ahead and just round that to the 100th. We're limited to 3 sig figs though, but we're okay. Gram per mole. And then oxygen, 16 gram per mole. And so hydrogen contributes 2.02 grams to the compound, oxygen 16. So if we add up, the formula mass of water is 18.02 grams for every 1 mole of water. every 1 mole of water. And so that's just a reminder of getting formula mass. Please be careful when your formulas contain parentheses. For example, let's do iron 3 carbonate. And so we want to make sure that we're interpreting subscripts correctly. There's 2 iron, 3 carbon, and 9 oxygen whenever you are calculating formula mass. Okay, so let's just work through some of these problems. All right, applying this information. Calculate the mass of 19 atoms of oxygen. All right, we're always starting with our given. Now, atoms. I didn't measure that. I must have counted that. So counted values, remember, do not limit sig figs. I want mass, gram. So I know my first job is to cancel atoms. Okay. Well, do I know the mass of an atom? Well, I know that the mass here could be AMU, but when in doubt, go to moles. When in doubt, go to moles. That is the heart of chemistry. So that can always guide you. Do I know how many atoms are in a mole? Oh my gosh, yeah. Avogadro's number. And I'm talking about, and you can abbreviate that, MOL. I'm talking about an element, so I know the smallest piece would be an atom, so this is a proper relationship. And I know that every 1 mole of oxygen is 16 grams. And so I've done what I need to do. For sig figs, this will not limit 4, 4. So my answer that I report should have 4 sig figs. And you're free to write this out if you would like, but I think scientific notation. And that is a reasonable answer because we're talking about just 19 atoms of oxygen. All right, so that would be the route that we would want to take, ladies and gentlemen. Okay, for example 2, now, we're going to compound. Can we pause for a second? Because I want to just talk about a formula a little bit more in depth. Now we know magnesium hydroxide. Well, we know we have 1 magnesium atom, or ion here, right, for every 2 hydroxides. That would give 1, this is a good time to go over this. This is ionic. So the smallest piece of an ionic would be a formula unit. And so if I had 1 mole of magnesium hydroxide, it would be Avogadro's number of formula units. That's the individual smallest piece of an ionic compound. So I could say that if I have 1 formula unit of magnesium hydroxide, well, I would have 1 magnesium plus 2, or I could say for every 1 formula unit, I have 2 hydroxide ions. Well, subscripts not only are the ratio of ions, but they also can be interpreted to be moles. If I have 1 mole of magnesium hydroxide, and I just chose to put that in the denominator, I could also put that in the numerator. 1 mole of magnesium hydroxide. Well, if I have 1 mole of this, then I would have 1 mole of magnesium plus 2, or 2 moles of hydroxide ion. So you can interpret the formula to be conversion factors as well. Okay, so let's get to problem solving. Determine the mass of hydroxide ions present in 0.00529 milligrams of magnesium hydroxide. All right, I want grams of hydroxide as my final answer. All right, let's take it a step at a time. First thing I definitely know, I'm going to get out of those milligrams. So, let's get to grams. And we know 1,001. All right. Now, I want to go to grams of hydroxide. I don't want grams of magnesium hydroxide. So, you have a choice here. And I trust that you're going to make the choice that makes most sense to you. Can I determine a relationship between grams of magnesium hydroxide and grams of hydroxide? Oh my gosh, I definitely can. If I get the formula mass of this, well, I have to find out how many grams are 2 hydroxide to get the formula mass. Now, what we could also do though, can't we always go between grams and moles? And absolutely. So either of these would be an okay route. And magnesium hydroxide is 58.32 grams in every 1 mole. And to get that, I did twice, and 1 oxygen and 1 hydrogen would be 17.01 grams per mole. So 38.02 grams of hydroxide. And check that out, I've gotten my answer. So as long as whatever you are using as a conversion factor is true, then you're fine. So what I get here, and this I would definitely assume is a measurement. So 3 sig figs, this will not limit us, and these both have 4, so I'm limited to 3.09 times 10 to the negative 6 grams of hydroxide. Okay, but what if you went this route? Okay, so now I've canceled and I have mole of magnesium hydroxide, but I just want grams of hydroxide. So my next step will be to cancel moles of magnesium hydroxide. And for every 1 mole of magnesium hydroxide, I can interpret the formula. There are 2 moles of hydroxide, and then every 1 mole of hydroxide would be 17.01 grams of hydroxide. And then what we will get, ladies and gentlemen, is the same answer. All right, so this reviews some of the fundamentals that we will need to adventure through this chapter.